Okay, what's your density question?
So my density question, first of all, as a bartender, I was like, man, now I understand why shots, when I layer them, why that makes sense.
That why
Um,
it works.
why I know why it works. Not just that they're thicker, they're just denser, which I
Right.
know means the same thing, but I get it now. It was about the Three Kings, and I saw that there was a question asked about it too, but I watched the trailer. Does it have something to do with the gold?
It has only to do with the gold.
Oh, but what is it? Like, I don't know. Like, was it in the car when they blew it up? Like, I don't know. I just don't know.
What's the lab about?
It's about density. And so there's a
Okay,
question that says, watch the trailer of the Three Kings 1999 movie and say what issue there is this density in the preview, in
correct.
the trailer. And I was
Okay,
like,
so you identified gold,
yeah,
and this is about density.
I
So
know, but
what's
what's
gold's
the
density?
thing? Huh?
What's gold's density?
I looked this up for the lab. I actually have this answer. Give me 2 seconds. The density of gold is, right, oh, 19.3 G-CM3
Not dash, divided by.
divided by, oh, okay.
That's grams divided by milliliters. So in the lab and well, I guess just in the lab, it talks about what density means. Did I give an explanation of of a suitcase? I can't remember.
No, it says to compare the densities of gold and helium, make sure they're the same units
No,
measured.
I mean in the intro stuff. Let me open it up. I gave you a shopping bag one. So you've got two in the introduction. It talked about having two grocery bags. They're exactly the same size grocery bag, but one bag is much heavier than the other one. So
Hmm.
the two bags, since they have equal sizes but different masses, that means one of them is much more dense than the other. So two objects with the same size but have different masses, that means their densities are different.
Yeah.
So really what we're talking about, the best non-scientific definition I've got for you is how tightly packed stuff is. All right?
But I don't know how that like applies to the preview though, the gold.
Okay, so 19.3. What
Uh-huh.
I'm trying to correct your unit mistake. So
Oh, sorry. I thought you
the
were.
unit is grams per cubic centimeter or grams per milliliter. So that's
Yeah.
a certain amount of mass per unit volume. So what we're saying is I have some stuff. How much space does the stuff take up? And if the stuff is a lot of mass and very little space, then it's got a high density.
Yeah.
Does that make sense?
Yeah.
Okay, so if you look up gold's density, and you did, and you came up with 19.3, did you look at anybody else's density or happen to know anything else's density?
I didn't happen to know, but one of the other questions asked like the density of iron, aluminum, lead, and lithium.
Okay,
And it's all different, but like lithium's like really, really light. It's not very dense,
all right.
and
It's it's like 0.53, somewhere around there, grams per
yeah,
milliliter. So how
yeah.
much different
Gold
is
is
the
pretty
den
hardcore. Like it's more than iron, aluminum, lead, and lithium.
did you do you happen to know water's density? Maybe I should have included that on that list.
No, but I did. I was doing some research for the question about the air carrier,
Yep. Oh yeah.
and water is a really dense fluid, but it's really massive. But it's like
No. No.
I thought it was.
No. Its density is one gram per milliliter.
Wait, what?
Yeah. Water's density is what all the other densities are based off of, and its density is 1 gram per milliliter.
Oh, I
So
definitely know.
you did need to look that up to answer question 8 because it's saying that the iron has a density of was it 7.7 or 7.8 grams per milliliter, and that means the water's density is only 1 gram per milliliter, but that doesn't seem to make a lot of sense, right?
Mm-hmm.
Because things that are more dense sink, and
Mm-hmm.
and we know the aircraft carrier that's mostly made of iron floats.
Yeah.
So why is this thing that's more dense floating on something that's less dense?
Displacement and buoyancy because of it.
Yeah, but that's not giving me an answer.
It weighs less than the maximum amount of water, which is what I came up with.
No.
Gosh, wow,
No.
I really kind of.
So, is the aircraft carrier a solid chunk of iron?
Yes.
No. No.
But there's a lot of solid chunks of iron making it. I just don't really know how they build them. I don't know.
Well, I mean, it's a boat. It's a big boat, right?
Yeah.
Is there an inside to it, or is the thing a solid chunk of iron?
No, you're right. There's other stuff in it.
Like what?
Seats and
Okay.
humans.
Excellent. I love it. Humans, seats. We like to sit on things. What else? They're not. They're alive humans. All the humans are alive in there, right?
Mm-hmm.
So they're probably breathing air.
Yeah.
So the inside of the boat is filled with stuff that doesn't have a density of anywhere near 7.7. Air's density is like 0.0001. But so the entire boat itself isn't just iron. It's actually mostly empty space. Does that make sense?
Yeah, I just was thinking, like the submarine, it would have made more sense to me in the beginning because I was like, okay, but I just pictured an aircraft carrier as this big thing that's shaped like a V.
Sure.
But I guess I was thinking out the compartments that are little chambers of,
All of those little chambers matter. Like,
okay.
I mean, a rowboat's made out of lots of different components, and what really matters is the fact that the inside of the rowboat is empty. So if I take the entire volume of the rowboat, which is the length times the width times the height, that gives me a volume, and then I could weigh the rowboat and figure out what its mass is, and if that number is less than 1, then that thing floats.
Sorry, she agrees.
I don't know. Is my daughter making too much noise?
No, she's not. I just think it's cute.
All right, just like, hey, no, stop jumping. So back to the gold thing. So gold's 38 times more dense than lithium. It's 19 plus times more dense than water. So when you saw the gold in the movie, what was it in?
It was in a basement. I mean, they're just.
Yeah, but what was it in?
I don't know. I honestly just.
Anybody else want to help her out?
A bag?
It was in a suitcase, right?
Yes.
It was in like a $5,000 Louis Vuitton suitcase.
Okay, I was thinking like grander. I was like, what room was it in?
Gotcha. Okay, so just stop for a second and think about this. What if that Louis Vuitton suitcase was waterproof? You filled the whole thing up with water, okay?
Okay.
Do you want to pick up that suitcase?
Mm-mm.
Why not?
Way too heavy. You just couldn't.
Okay, so now it's filled with gold, and gold is 19 times heavier. How much does that suitcase weigh?
A lot.
What do you drive?
Tahoe?
Okay, so it weighs a little bit less than your Tahoe.
Oh my gosh.
And if you watch the whole trailer, what happened with that suitcase at one point?
It got blown up?
Nope.
It ripped.
No, didn't rip. The strongest man in the universe, according to that movie, Mark Wahlberg, was running while carrying one of those suitcases and then scooped up a small child. So he's carrying a car in one hand while sprinting and picking up a child in the other hand because he's obviously like the reincarnation of the Hulk, evidently.
Okay, I was really distracted because it was George Clooney and Mark Wahlberg in the same preview. So you're like, what kind of room was the gold in? What were they doing? I'm like, I don't know. I was trying to pay attention, but it's just very distracting.
That sounds like a personal problem.
No, but honestly, I just genuinely that makes a lot of sense now. I did not see that.
Is dense just another word for heavy?
Absolutely not.
Okay.
Dense is not another word for heavy. So, let's see, I'm trying to think of a good example here. Did you hear about that guy who he was having a heart condition, but he was so overweight that he couldn't fit through the door of his bedroom, and they had to cut a hole in his house and pick him up with a forklift to take him to the hospital.
Oh my gosh. Yeah.
Is that guy heavy?
Yes.
What would happen if you threw him into the water?
He would float.
He would float, like really float, like he couldn't drown, float. So that means that man's density, although he's very heavy, his density is much, much less than your density. So density and heavy are not the same thing. Heavy just means there's a lot of mass there. Density means the mass is compacted. Does that make sense?
Yeah.
Yes.
So if you have a gallon of milk in one of those plastic jugs, and you pick it up, it weighs about 9 pounds. Okay?
Hmm.
What if it's empty?
It's very light
Why?
because it's full of air.
And air's density is 1,000 times less than that of water.
Yes.
So that's all we're talking about. Density literally is just how tightly packed the stuff is, regardless of how big it is. So, like a wedding ring, a gold wedding ring has a mass of around 7 grams. Is that thing heavy in your hand? For a wedding ring, for something that's that small, it's pretty heavy, right?
Yes.
Okay, so that means that stuff is tightly packed. But I wouldn't say it's like heavy. I mean, it only weighs, stop, it only weighs like 7 grams. But what if instead you were holding, oh, I don't know, let's say a gold brick that was a foot long and 3 inches wide and 3 inches tall? How much would that weigh?
A lot.
Like 85 pounds.
Hmm.
So when you're watching that preview, George Clooney is like the second strongest man in the universe because at point early in the movie, he just grabs one of those gold bricks with one hand, pulls it out, and he flips it around in his hand like he's spinning his cell phone around. I don't know about you, but an 85-pound dumbbell for me is something hard to move around.
Yeah.
So
that
Go
is a piece of black coal
yeah,
will be denser than a piece of the what they call that light colored coal.
sure. You can just call them light coal and dark coal, or sorry, light coal and dark coal. One of them is going to be more dense.
The exact same size, but one is going to be denser than the other and heavier.
The one that's more dense, even though they're the exact same size, the one that's more dense is going to be heavier. How about this? In 1982, they changed the composition of the penny. Pennies before 1982, between World War II and 1982, are solid copper.
Hmm.
Pennies after 82 have a very, very thin layer of copper around a penny that is made of zinc. Okay?
Okay.
Have you noticed that like the shiny new pennies seem to be a little lighter than the old dirty pennies?
Yes.
That's why. The pennies are exactly the same size, but zinc's density is a couple of grams per milliliter less than copper's density. It's about 20% less dense, a little more, maybe 22% less dense. But they're the exact same size. So if they're the exact same size and one weighs more than the other, then the heavier one is the more dense one.
Okay.
So you could think about it with people. Like the NFL draft was last week, and those guys get moved around in Indianapolis like they're cattle. They get weighed and pinched and poked and measured and all kinds of different things. And one of the things that they're measuring is percent body fat. So they'll have guys with percent body fats down to like 3%. Tell me about the density of that guy's body compared to a normal person's body.
Well, I think he'd be a lot denser because he's all muscle.
Because he doesn't have a lot of fat on him, unlike that guy that they had to pull out of his bed in a forklift. So when I was during my undergrad, I've been a lifeguard most of my life, and during my undergrad, we had a guy who was drafted in the first round by the Denver Broncos, and his name's John Mobley, and he played for like 6 or 7 years. He was a very good player, best player. Well, probably the second best player to ever come out of my little college called Kutztown, which is in eastern Pennsylvania. At Kutztown, to graduate from college with a bachelor's degree, you were required to take a swim test because 50 years ago they had a weird thing happen where they graduated, just had a regular graduating class, and during the course of that summer, 12 of their graduates drowned. So the college said, well, forget this. If you want a degree from us, you have to learn how to swim. Well, John had a problem. He never swam as a kid, and he had 4% body fat. So when he went into the water, what happened to him?
He sunk.
He sunk like a rock. So I had to teach him that he could just use his ridiculous amount of strength and speed to overpower the water and just fly through it like an airplane. And so that's what he did. He literally just beat the water up and didn't need to worry about any of the other things. Like the Olympic guys, they're not floating out there. They're moving so fast that they're generating some buoyancy for themselves. And so that's what we did for him. So things that are more dense than other objects, if they're the same size, they're heavier. Does that make sense?
Yes.
Okay.
Is it as easy for somebody that's super muscular to snorkel than, stay the normal human?
Snorkel?
I don't know. You're saying that like if you're, less dense, you float better, which makes a lot of sense. But like you're talking about these people who, with a lot of muscle, they have to, work kind of harder to stay up there.
Yeah.
I don't know. Does it make you, for example, like, can you snorkel less easily than somebody who has more body fat? I mean,
sure. You'd have trouble keeping your body when you're snorkeling, you're probably like looking at stuff and slowing down and like,
you're just like floating.
yeah, you're basically just floating around. So that guy I'm talking about, John Mobley, he'd be a terrible snorkeler.
Like would he not be able to just relax and like
no, he
lay
couldn't.
in the water? He would
Totally,
just
completely impossible for him to relax in the water because his density is like 1.1. So he's 10% more dense than water, so he just sinks. Not like a rock, but he sinks like an object 10% denser than water. I mean, he jumped in the water and he went right to the bottom. And I jumped in and grabbed him and pulled him up and was like, all right, this is going to be fun.
Yeah. That explains a lot. Do you ever watch the show I Shouldn't Be Alive?
No, but it sounds a lot like Darwin Awards.
No, it's not like that. It's a Discovery Channel, and it's people who've gotten into really life-threatening situations like kayaking or, anyways, this one guy was skydiving with his friends, and the plane crashed, and they all decided to jump as it was crashing, and a lot of the people didn't survive. But he was one of the ones who survived, but he was like kind of overweight. He wasn't huge, but he was, bigger dude. And he was in the water for like 3 days, but he survived because he floated. Yeah, sorry, random. I go.
Where was the accident?
It was like close to New Zealand or something, I think.
So he probably also survived because he didn't lose body heat like the rest of the people out there.
Yeah.
That might not sound like a dangerous thing, but if you go in the water in the North Atlantic, you got about 3 minutes before you probably saw Titanic.
Of course.
So he died because he got cold, and that's exactly what would happen. If you were in that water, you would get cold very, very fast. Okay, what else you got?
Well, any questions that you would like to quiz us on subjects we do need to know for the exam would be great. I'm kind of interested in the petroleum. So I understand the good coal that we're using is about exhausted. So we've moved to
There's no such thing. Can I stop you for a second? There's no such thing as good coal. There's bad coal and badder coal.
Well, it says the good coal that produced more energy per unit
Sure.
than the coal. That's, I'm just referencing the book, but that we've moved to petroleum. Is petroleum just as harmful? Is it at the same level in the earth as coal?
So the book talks about the type of petroleum that we use for electrical production, and it's basically all natural gas. When you look at that fractional distillation tower, do you remember that thing?
Yes.
So it's what page is that thing on?
It is on 169.
Okay, so you've got crude oil, and so crude oil comes in, it goes into that boiler, and they heat the crude oil up to like almost 400 degrees Celsius. Okay, so that's very hot. This entire container, the fractional distillation tower, is a closed system. No oxygen can get in there, because if it did, this thing would explode like a Roman candle, like a really, really big Roman candle. So what you're doing is you're taking this crude oil, which is exactly what it sounds like. They just literally pump this stuff out of the ground. Okay, they did filter it, so there isn't actual dirt in it. But all of the different liquids that are in that crude oil have different length chains. So when you heat this stuff up, you can get it to be less viscous, less sticky, and so some of it actually turns into a gas and boils. And so almost all of it turns into a gas and boils. The only stuff that doesn't boil is stuff that have carbon chains that are 20 or greater, and that's asphalt. And that's literally the asphalt that you drive on. So that everything that we're driving on, unless it's a concrete street, that is crude oil, the bottom of the barrel for crude oil. So what's going to happen when we run out of fossil fuels, besides the fact that it's going to be more difficult to drive around in an internal combustion car? We're not going to have any roads to drive on, because concrete costs an incredibly large amount of money. That's why only some roads are concrete-based roads, and all the rest of them are asphalt. So we'll probably end up having like freeways that are made out of concrete, and then the rest of the roads around will be just gravel. That's going to seriously slow you down, right? When Highway 35 is no longer a highway and it's just a well-traveled gravel road. That's going to be a problem for us. I'm not going to be used to that. Maybe we'll have flying cars by then. So as the liquids, the crude oil gets further and further away from that boiler, the longer chains turn into a liquid, and we siphon those things off. And so you can see on that list, you have these lubricants and then different types of gasoline. Like it says gasoline there next to the jet fuel, but it's really saying that's gasoline for really big diesel motors and for jet engines. And then we've got other types of gasoline that come off with the refinery gas. And then there's regular diesel for a car that you'd be driving, some more different type of jet fuel. And then that's regular gasoline, that second from the top. And then the one at the top that says refinery gases, that's natural gas. So that's the gases methane, ethane, and propane that they talked about in the first chapter.
Okay, can I ask a stupid question right there?
It's not a stupid question, but go for it.
Crude oil goes through the boiler, and at one time in a tower, are these things being produced at one time? Or do you have to leave it in there and then it, produce jet fuel at one time, produce diesel at one time?
It happens. It happens all at the same time, and you're not producing any of it. You're just separating them out. So the crude oil is a mixture of all those things. So this distillation tower isn't producing diesel or producing gasoline. It's separating the gasoline from the asphalt. It's separating the jet fuel and the diesel from each other. That's all it's doing.
Oh, I get it.
If you grabbed if you had a barrel of crude oil and you took the lid off of it and you stood there, the gas would just come out. Methane gas, ethane gas, propane gas, all of those things would eventually just filter out of that because they're gases at this temperature. This is just making the process happen faster, as well as separating all the different carbon chain lengths into their own barrels.
Okay. Okay. I'm actually a daughter of miners, of a miner.
Oh, yikers.
Yes.
Mining
Well,
what?
my dad was a silver miner along with my grandpa and many of my uncles in Idaho. But he got a piece of silver in his eye. It was in a silver mine. And he went, got retrained, and now he's an engineer. But pretty much all of them are still working in the mine up there.
Well, those mines are infinitely cleaner than a coal mine would be.
Yeah, that my grandpa did still die at 50 from black lung. So.
Oh, wow. That's
Yeah.
horrible.
That is terrible. It's amazing they're all still up there in that too.
Yeah, I don't understand that.
Have you ever seen the inside of a mine?
Oh yeah. They've got mines along the Oregon coast that you can go through, and then I was in West Virginia on a rafting trip, and we went through a couple of old mines, and they're terrifying.
Absolutely terrifying.
They're a lot more confining than I expected. I expected like, I don't know, several feet of space on all sides, and no, you're cramped.
There's very little there's very little ways that a person can make a living up there in the hills unless you have money. So that's pretty much what a lot of people have to do to take care of their family.
Yeah. Okay. What else you got?
Yeah, it's right now. Not right now.
Marilyn, did you have a question or was that accidental? I guess that was accidental. Something else you guys want to talk about from 3 or 4?
The covalent bond energies, I think, are kind of difficult to understand.
Again, we're not doing any of those covalent bond calculations, so you don't need to do any numbers with that.
So understanding how they're broken and formed, we don't need to worry about that.
The only kind of question you could get associated with that is something I guess I'm kind of hoping that you understand, but we can talk about it. So when you want to break something in chemistry, if you want to break a bond, that takes energy. And then when new bonds are formed, that gives you energy back. So whenever a bond is broken, you're forced to input some energy into that. And when the product bonds are made, you get energy back from that. And depending on which of those processes, the breaking or the making of bonds is greater, that determines if the reaction that you're looking at is going to give you heat or make you put heat into it or energy into it. Does that make sense?
So is that at all related to, you know how at the beginning of the chapter we learned about the first law of thermodynamics, that you can't destroy energy?
Correct.
So it's the same thing? It doesn't get destroyed, it just gets broken.
It gets transferred into another way. So like if you, let's say that you're, I don't know, holding your cell phone up, and then you drop it and it hits the ground. When you were holding it in the air, it had a certain amount of energy in the form of potential energy. Does that make sense?
Yes.
So if you lifted it up higher, it would have more potential energy. Lower, it would have less potential energy. So you know it has a certain amount of energy because you're holding it there. When you let go of it, it doesn't have that potential energy once it's sitting there, not moving on the floor anymore. Where did that energy go?
Maybe it's kinetic energy.
Okay, so
Or it came kinetic.
as the phone fell, it fell through the air, and the potential energy was converted into kinetic energy. So, but now that the phone's at the ground and it's not moving anymore, that kinetic energy is no longer in the phone, but it's still out there somewhere. Where did it go?
Is it on the ground?
Part of it is on the ground. The spot where the phone hit, it's not going to be much because dropping a cell phone from a height of 3 feet isn't a lot of energy loss, but those molecules on the carpet or the linoleum or the concrete or the grass are actually moving faster because you just hit them. Does that make sense?
Yes.
Also, as the phone fell through the air, it hit air particles and caused them to move faster. So even though the energy isn't in the phone anymore, it's been transferred to the molecules that it hit along the way until it stopped, whether they be air molecules or carpet molecules. Does that make sense?
It does. And this is similar to that Newton's cradle.
Sure.
And I was kind of confused about that because the ball would go down and the energy would be released when it hit the first ball.
It transfers into that first ball. Yep.
And then does it go through or does it get stuck
It
at the
transfers.
very center ball?
No, it
Because
keeps
Go ahead.
transferring from one ball to the next, and that's why the ball on the far side starts to move and flies away from the rest of them. But as it's
Okay.
doing that, I mean, have you seen one of those Newton's cradles before?
I have.
How do you know that it's actually moving if you weren't looking at it?
You could hear it, right?
Sure. If you're hearing it, that means air particles are hitting your ear in a way that they shouldn't be doing if they weren't given energy. So when you pull that ball back the first time and you let go of it, right before you let go of it, it has a certain amount of potential energy. And that Newton's cradle only lasts for a certain period of time. Part of it is because as it's traveling through the air, it's making those air particles move faster. So the air particles are actually slowing it down. They're transferring, the ball is transferring its energy to those air particles. When it strikes the ball, this is something that a lot of people don't get, but when you clap your hands, you are actually forcing the air that's in between your fingers and your palms to scoot out in between where they're getting smacked really, really fast. Does that make sense?
Yes, I get that.
Okay, so the reason that your clap makes so much noise is those air particles actually just broke the sound barrier. They're trying to get the heck out of the way because they have to. And so when those balls in that Newton cradle, right, I mean, there's not very much actual contact surface with those balls because they're spherical. But the last little bit of air that's in between those balls right before they make contact, that air particles, they have to scoot out of there so fast that they cause a sound to be formed because they're moving that quickly. And so then that energy from that first ball that didn't get turned into energy for the air scoots into the next ball, and that ball hits the next ball, which hits the next ball, which hits the next ball, which hits the next ball, and then that ball moves out away from the rest of them and starts running into air particles again. And then it swings back down, running back through more air particles, and then hits that next ball. So how come it doesn't keep going on forever?
Because energy is absorbed by the molecules around it, the heat, the sound, everything.
All
It
those
runs out of potential energy.
all of those air particles are now moving faster. So their kinetic energy has gone up. So if their kinetic energy went up and the energy of the universe can't change, then it came from somewhere, and it came from that initial potential energy of that ball being picked up. So even if you did this in a vacuum and there was no air to be moved around, when those balls run into each other, the actual atoms that are inside of those steel balls start to move faster. And so that steals energy. So it would take a lot longer for it to stop moving if it was in a vacuum, but it'll still stop moving.
I have a question.
Go, Casey.
So if it was in a vacuum and there was no air to be moved around,
Yeah.
would you still be able to hear it?
Nope, absolutely not. Of course, it would also suck for you to be inside of there because it would kill you.
Right. That's true.
Did that answer your question, Cami?
Yep, that did.
Let me put a little bit more on top of that. When you take a charcoal briquette, you get energy out of that, right?
Yeah.
So when what happens is let's do this. I'll put up a where's the whiteboard? There it is. Share the whiteboard.
Did you miss me?
All right, I need my pen here. Why isn't that on? Okay. So a charcoal briquette is basically just solid carbon. They're just carbon atoms. They're kind of stuck to each other, but they're not actually chemically bonded to each other. And when I burn a charcoal briquette, it's because, whoa, what was that about?
Are you writing yet?
Yeah, can you not see that?
No, I can
No.
swipe.
What are you guys seeing?
Just a whiteboard.
Tiny little pen up there, like a little outline of a pencil or something.
I just have a whiteboard.
There's no red C there.
No.
Nope.
Huh.
Okay, I see it now.
Okay, me too.
Okay, that was really weird. Okay, so let's do. So we've got carbon in its solid state, and then how do you burn something? What do you need?
Fuel and combustion,
So carbon is the fuel. What else do you need?
oxygen.
Are we okay with that? Oxygen is one of the diatomics, so it's always found as O2. And then when you burn this, you end up with carbon dioxide gas, okay? Let me redraw this, sorry. I'm also going to redraw this over here. S, and then I'm going to do a CC0, CZ0. Okay, so when this chemical reaction happens and you're watching the little charcoal briquette burn, what has to be broken?
Oxygen.
Those oxygens are connected to each other with a double bond. And to get those oxygens to connect to the carbon, the first thing that they have to do, their own bonds have to break. Okay? So that takes energy. We all right with that? So it takes some energy to break those two bonds. But on the other side of the equation, when this bond and this bond and that bond and that bond form, you get energy. Okay? Which one of those two things is greater?
Greater. It takes energy to get energy. See.
Tell me what you're using the charcoal briquette for.
Heat.
Okay, so you must be getting a bunch of energy, right? I mean, the only reason you're using the charcoal briquettes is to cook food. So which one of these is more? You putting energy into it to get it to burn, or you getting energy out of it?
Oh, putting energy in, I think. Like, don't you get a lot less energy?
Getting energy, you have to burn. Yeah, okay. Okay.
the entire reason you're burning the charcoal briquettes, so it will give you heat, right?
I think I misunderstood the question. I was just thinking like, never mind.
So is this a formula we need to know? Because I'm lost with the diatomic thing you said earlier, the two.
That's something
Oxygen?
from chapter 1. Oxygens and six other atoms are always found in a diatomic form.
Okay, and okay.
When you can't go get a single oxygen atom or a nitrogen atom or a hydrogen atom, they always come as pairs. But O2 you're breathing right now is in the form of O2 and not in the form of just O's. So my point with your covalent bond question was, and the bond energies, is it takes a little energy to get this bond to break. And when you make this, you get lots of energy. How do you know that? Because I light the charcoal briquettes with a match, and then I step away from it, and I get a whole bunch of heat. So this is producing more energy than I put into it. Does that make sense?
It does.
Okay, so sometimes
And
this is what happens. Sometimes I have a chemical reaction that gives heat off, and that chemical reaction is called exothermic. But the reason is because the covalent bond energies of the reactants is less than the covalent bond energies of the products. So the products give me a lot more energy, and my reactants only take a little bit of energy to get to be broken.
and this is why petroleum is so popular.
It's because petroleum is some number of carbons with some number of hydrogens, and they'll produce, when I break their bonds and I make the carbon dioxide and water, I get a lot more energy out of it. Yes. They are stored energy. I mean, where did they come from? Where does fossil fuel come from?
The earth?
No. Earth.
What are the fossil fuels? I mean, your fossil fuels, you're talking about coal and
Yeah, but where did that stuff come from?
it came from vegetation that's been compressed for lots of years, correct?
Correct. So a forest died, got covered up, massive volcano happened, some kind of earthquake, and literally a forest got covered up with a bunch of dirt and buried, and it's been there for 1,000,000 years.
Mhm.
So those trees have a lot of energy in them. They have a lot of energy in them, and you know that because the trees have been absorbing sunlight and converting that energy into sugar and carbon dioxide. And so when they get covered up and decay of their own accord, they will turn into highly energetic molecules.
So why are they so bad if they're all organic?
Organic is kind of a silly word, especially for chemists, but this is the reason that they're bad, because they all produce carbon dioxide. So why is that a bad thing? Based off of the chapter 3 stuff.
Well, I know that carbon dioxide is good, but I also know that it's bad because of
Why do you think
the
it's
ozone that's holding
no,
it down,
no,
right?
no. Why do you think it's good?
Because carbon dioxide we use in our planet for our plants use it.
Okay.
Does it help block the heat that reaches Earth?
Okay. That is the best answer you could give, is that carbon dioxide allows the Earth to be warm. So in chapter 3, they talk about bending and vibration and breaking of bonds. There's a picture of it on page 120. So what happens with the radiation that comes from the sun? Can somebody tell me what happens?
Well, I know that ozone pushes some of it away, but some of it goes through and then it bounces off the earth and goes back up. But if we have too much of a blanket of ozone, it won't let it release, correct?
Ozone doesn't have anything to do with it.
Well, but
Okay.
some of it is absorbed by the earth. That's what warms us up.
Most of it's absorbed by gases in the atmosphere.
The greenhouse gases kind of break up the energy cycle.
Was somebody talking?
Can you not hear me?
Or was that you?
Yeah, sorry.
It sounded like
Yeah.
you're at the end of a very long tunnel.
Oh, well, I'm in the middle of moving, which is why I haven't been around. My house is very empty right now. It's our last day.
It sounds very
Sorry.
empty.
But our internet's not getting transferred over until tomorrow, so I decided to come back here and use the modem in my computer in an empty room to do this.
Gotcha. Okay.
But a lot of the greenhouse gases absorb that energy, right? So instead of it being harmful and like the ultra UV rays getting down to us, it gets absorbed by the gases, right?
Sure. Yeah.
Okay.
So are we all pretty happy with the temperature of the planet in general? Pretty much, right? I
I
mean,
know, yeah. Yeah.
you're okay with where you're living in a temperate zone, but what would happen if Oregon's average daily temperature was 80?
It would look like Southern California. Or,
So what would Southern California look like?
oh gosh.
The desert.
Okay, how many people live in
Death
Southern
Valley.
California? Where would they have to move to?
Oregon.
Oregon. What does California do really, really, really well?
Pollute the environment.
No, you're actually completely incorrect on that. California is the cleanest state as far as pollution controls go.
Why is it so brown when you fly in there then? Like you can see a layer.
Why is that? You mean the air?
Yeah.
We don't. It's the same reason the Dalles gets like that from temperature inversion stuff.
Oh, gotcha.
Nobody wants to tell me what California does really, really well, besides make movies.
Green energy, I think, is that where you're going?
Nope, I'm going with they grow vegetables. If you're eating a vegetable, it came from California or Mexico.
No, I thought avocados. That was the
There you go. Avocado's good choice. But what would happen if Oregon's 80 and California is 100? What happens to all the vegetable production?
They dry up and die.
We don't eat. So when you start taking carbon dioxides and putting them in the atmosphere, can you see me drawing on this picture?
Yeah.
Yeah.
The more carbon dioxides are in the atmosphere, the more radiation when it comes down from the sun. Some of it just gets reflected off the exterior. Most of it hits the planet, and then a lot of it is reflected back. When it gets reflected back, if it runs into a greenhouse gas, it never leaves. It stays here. Is that a problem?
Yes.
Why is that a problem?
Because it causes global warming.
Because now the planet's temperature, since it has more energy in it, it got warmer. When that continues to happen, then you're going to have massive climate change. The planet doesn't care. Let's start with that. The planet doesn't care that there's anybody living on it. It is literally a rock flying through space. We care because if we change climate, meaning long-term weather patterns in regions of the planet, we will mess our entire economy up because we've been growing vegetables in California and then we won't be able to. So where are we going to grow them? Is that something we can just pick up hundreds of millions of acres of farm and just quickly move them to, I don't know, eastern Washington? It's not something we can do quickly. The issue is burning fossil fuels increases the CO2 in the atmosphere, making the planet warmer. It's like you going outside on a day when it's 80 degrees and putting on your ski jacket. you're not comfortable. It's not good for you. This whole thing isn't good for the entire planet. So if you're asking why the fossil fuels are bad, it's literally because they're warming the planet so much that we are going to destroy all the places we can farm.
I mean, I get that. I guess my question was, when somebody is in the backyard burning creosote covered ties,
Yeah,
I
that's
can understand why that would hurt the earth. But sometimes I do wonder why coal that comes directly from the earth, that no scientist or chemist got a hold of and added some crazy chemical.
no scientist or chemist would ever add a chemical to coal.
Well, that's my point. That's my point. They didn't, so I don't know why. You know, sometimes it just seems odd. I get it that it does. I completely get that. It's just kind of weird. Like I said, I can see a chemical hurting the earth, but something that is made by the earth. It's
Cami,
but,
cyanide is made by the earth. It's a completely organic molecule. How much do you want to eat?
yeah, but we're not burning cyanide.
What I'm saying is you're saying it's from the earth. That doesn't mean that the thing is good. Arsenic is from the earth. Cyanide is from the earth. Mercury is from the earth. Being from the earth doesn't mean it's good for us. It doesn't mean it's good for our environment. Does that make sense? Okay.
Yeah.
Nobody. I mean, a rattlesnake has got poison that came from the planet. That is an organic molecule. Organic doesn't mean good. When you take fossil fuels and you burn them, you make carbon dioxide. It doesn't matter where it came from. None of that matters. All that matters is your end product is carbon dioxide. That's all that matters. Just because it's from the earth doesn't mean it's a good thing or a bad thing. If you make more carbon dioxide, the temperature of the planet goes up and we die. There is nothing else to be said about it. Did your bond energy question get answered?
Yes.
Okay. What else we got?
Okay, so in chapter 4,
Yep.
table 4.5, the octane ratings.
4
Yeah.
point. Yep. Go for it. Octane ratings. Yep.
It talks about, the different types of gasoline you buy when you go to the gas station.
Sure.
Your, premium plus, regular, whatever. Where do those come into this table on 4.5? Like,
What page is that on?
180.
180.
What's the when you go to the gas station, what molecule are you hoping to buy? How about what's like a chemical name for gasoline?
My brain is not working.
Can you see what I wrote?
Oh, yes.
Does that name rings a bell, right?
Yes.
What's this prefix mean?
8.
That's gasoline. That's the chemical formula for gasoline. So the most common way, or the way that most people would draw this out, is there would be 8 carbons all connected to each other in a line. 2, 3, 4, 5, 6, 7, 8. And then around those carbons are going to be hydrogens. It's really hard to draw like this.
Looks like a centipede.
Okay. Everything that went through that fractional distillation tower from whatever page that was that we talked about earlier, 169. They all look like this, but they're different lengths. So for gasoline, it's 8. But this molecule is actually really, really bad to run through your car because it's the temperature at which it catches on fire is lower than what you want it to be because your motor is hot, and so you only want it to burn when the spark plug sparks. So what they did is they took the molecule and they cracked it and they made this molecule. Oops, sorry. What is different about this molecule and the molecule I have written above it?
That's where your octane comes in at.
No, this one's octane. This one up top's up to octane. What's different about these two molecules? How about this? What's the same about these two molecules?
They have 8 carbons.
They both have 8 carbons and they both have 18 hydrogens. So this one is called, the one up top is called octane, and they made this a nice easy name and called it isooctane. What they were saying is we took this octane molecule and we disassembled it and we put it back together a little bit different. And the reason is because this molecule doesn't burn until the spark plug in your car sparks. And that's really good because if it burns when it's not supposed to burn, it can damage your motor. And when you go to the gas station and you buy higher grade gasoline, you're getting more of this isooctane stuff. And when you buy the lower grade gasoline, you get more of this regular octane stuff.
So that's why when you have like a luxury car and it tells you do not put anything in it that's super, that's why.
They're trying to make your engine perform at its maximum ability and make sure it doesn't damage itself. Yes. When you go to like if you watch a car race, they're all running on 100 octane, which is just this isooctane stuff. They make sure there's none of this in it. And that gasoline is considerably more expensive because it's just the isooctane.
So if you put regular gas in a car that specifies it needs super, would it actually break down?
No, it wouldn't break down, but it would need maintenance more often than they would expect it to. The only cars I've seen have that designation are like Audis and BMWs and Mercedes. I haven't actually seen any other cars say that. I mean,
No, actually, so
Go
Jared
ahead.
just got a Volt and it needs premium. And it's kind of ironic because it's like half electric, half gas, right?
Right.
But it needs premium gas.
Yeah, my guess is that's just them conspiring with the oil industry to get you to buy higher
Yeah, I'm
expensive
like, what
gas.
is it?
Yeah.
Oh, it was kind of funny, honestly.
The other thing with the octane thing is there've been 2 gas companies caught selling 87 in their 92.
Hmm.
So you're thinking you're putting in 92 octane and really you're just getting regular gas. Texaco got caught doing that, and then they got sold, and then Chevron got caught doing that. So you might not actually be getting what you want anyway. But the one definitely makes it so your car has less problems, especially if it's an older vehicle or been driving for a long time. This isn't going to affect a new car unless there was a manufacturing defect. It's going to affect an older car that this has happened to, and continuous stresses on the pistons and the camshaft and the bars. I mean, do we know what a? Let me stop this for a sec. I think it's this one. This one? Is it this one? Just Why is this so? Yeah, that's not even close to what I was looking for. I just want this one. Oh, it took me to Pinterest. I hate that. Let's find one someplace else. Giphy? Yeah, Giphy should work. What are you guys seeing right now?
Black screen.
Black screen.
Oh, there we go.
This is your car unless you drive a diesel. This is a 4-cylinder version of your car. So all 4 pistons are doing different things at the same time. And so what you have are a way to get gasoline and air in, and then a way to get exhaust out. So you can see there's each one of those things that are moving up and down are pistons. And then above them, you can see a blue and a red valve, and they're opening up at different times. Everybody seeing that?
Mhm.
So the one of the valves is letting in a blue mixture, which I'm assuming is gasoline and air. And then the other valve opens up and lets the black exhaust out. All right. So at any given time, you're going to see some red-orange, and that's the explosion of the fuel burning. So how often is that happening at any given time? How many of the cylinders are burning?
1.
Just one. So when you're driving your 4-cylinder car, only one cylinder is actually pushing the car at any given time. All right, so what has to happen, just watch one piston for a second, just that first one. How many times does it go up and down before there's an explosion?
3.
2.
Oh.
There's a blow up, up, down,
Oh, yeah.
up, blow up, down, blow up. So what happens is the air and fuel come in, and then the piston goes back up, and then the spark plug blows that gas up, and now it's all exhaust. And then when the piston comes back up, the exhaust valve opens up, and then all the exhaust gets sent out the tailpipe. So what would happen if the piston exploded at the wrong time? The gasoline exploded at the wrong time.
Destroy your engine.
So you see how 2 of the pistons are going up and 2 of the pistons are going down at any given time? What if one of the pistons that was trying to go up exploded its gas before it got to the top? That would cause that piston to try to reverse its position and go the opposite direction that the other 3 pistons are going. And down at the bottom, down here, this assembly, this is the rod, and then this thing here, this long thing that they're all on, is called the camshaft. This turns up and down motion into rotational motion. You would break this pin that was down here if this exploded at the wrong time. And if you put bad gasoline in your car, you can get it to explode at the wrong time. If you've been in an old car and it pings and knocks, that's the pistons blowing up at the wrong time. That's putting stress on this portion down here, on the camshaft and the rod and the piston, or and the pin. And when that happens enough times, one of those things is just going to break. And when that happens, then the engine's completely shot. So who was that asked that question?
That was me.
Okay. Does that answer your question?
Yes, thank you.
Sure. What else we got? Nothing? Aurelia, do you have anything you want to talk about?
No, kind of touched on the things that I was a bit confused about. So
Okay.
I think I'm good.
Marilyn, Deanna, Cami, Casey, anybody?
Okay, I have one more question.
All right, go for it.
Okay, so biodiesel.
Yep.
Do they make like biofuel for normal cars, or is it just diesel?
It's just diesel. The diesel motor is more well built than a gasoline motor, and it can handle exploding fuels of different qualities. That's why there isn't like 3 different types of diesel fuel. The diesel motor almost doesn't care. Does anybody know what the guy who invented the diesel motor originally designed the diesel motor to run on?
Or
What?
nothing. I was just thinking about the chapter.
No, nobody. So when Rudolf Diesel invented his diesel motor, he originally designed it to run on peanut oil. So your diesel motor will run on peanut oil. You would need to modify a couple of things to make sure that the diesel never coagulated into a solid or a waxy substance, just to make sure it stayed warm. But it ran on that. And that would have been, I mean, you asked me about biofuels. Biofuels are just fuels that can be produced by a biological organism in a sustainable way. So we could grow peanuts and then we could squish them and we could take the oil out and we could sell people the oil and they could put it in their diesel car and run off of it. That would be a biofuel. Does that make sense?
It does, yeah. My family has a restaurant, and we have people that buy the nasty grease that comes out of our grease traps to make biofuel with. So I was just curious why they don't put it in normal cars, but that makes sense.
When you, well, that's really it. It's regular cars can't handle. They have to have. They're very temperamental. They need a specific kind of gasoline, and if they don't get that, then they do not run well. The motors will break, and diesels are basically don't care. They just drive. I mean, like, why do semi trucks have diesel motors in them? Because they're hard to break. They're just more well built.
Okay, thank you.
Yeah, that fry oil thing is funny because, like, when people first started thinking about doing that 20 years ago, you could just go to go to like a McDonald's or something like that and tell them, hey, I'll take your fry oil away. And it'd be great because we have to pay somebody to take it. And at that point, when people were being paid to take it, they were literally just taking it and dumping it in a landfill. And then we realized you could just filter that and then you could burn it in a diesel motor. And so people started doing that.
Yeah, that's why all the buses in like Gresham smell like French fries.
Yeah.
Kind of gross.
Or not. French fries are good.
I suppose, unless you cook them all day long, and then it's kind of gross.
Okay, you're right. I worked at Wendy's for a long time.
Yeah. Yeah.
Wait, what's a long time? How long did you work at Wendy's?
Like 2 years in high school.
That was my first job. That's why I asked. I worked there for
Yeah, it was my second job. Like too many triple cheeseburgers.
I actually loved the fries and the honey mustard sauce.
No, I mean they're as far as fast food goes, I would go there before I would go other places. So that's probably a good thing. Anybody else got anything more? No? All right, I guess I'll just call it. And I'll see you guys, what is today, Wednesday? See you guys on Monday?
Yeah, Monday. Bye.
Have a good
Bye.
Bye.